All right, let's kick things off with a classic exam question that honestly trips up a ton of infrastructure admins during those late-night study sessions. Do you actually know the exact difference between 1n/1d and 1 and 1d fault tolerance? I know, it looks like a simple typo, right? Just an ampersand instead of a slash. But in the world of Nutanix cluster design, mixing those two up on exam day, or, worse, in a production environment, can lead you to completely miscalculating your hardware requirements.
So welcome to this explainer. Today, we are diving deep into exactly that. NCP-MCI 7.5, Objective 4.3, Replication Factor and Cluster Fault Tolerance. This is an in-depth exam prep breakdown specifically tailored to help you completely crush this section of the certification. We're going to cover the underlying logic of how Nutanix protects data, so you're not just blindly memorizing numbers, but actually understanding the engineering behind them.
Here is our blueprint for today. We will quickly cover why resiliency matters, walk through fault tolerance and replication factor, discuss node, block, and rack awareness, hit those sneaky exam traps and edge cases, and wrap up with the key facts you absolutely need to memorize.
Okay, Part 1. Why resiliency matters. Focusing on baseline cluster design.
Before we get into node minimums and complex matrices, we really need to ground these technical acronyms in something physical. Nutanix clusters are, by design, built to survive hardware failures without losing data. But the extent of that survival? Well, that's entirely dictated by your baseline resiliency configuration. You're going to see two terms everywhere: replication factor, or RF, and fault tolerance, or FT. Think of replication factor like your architectural blueprint. It simply dictates how many physical copies of your data actually exist on the storage containers. Fault tolerance, on the other hand, is kind of like your cluster's structural earthquake rating. It tells you the exact number of simultaneous hardware failures, whether that's disks, nodes, or entire blocks, that your system can take on the chin while staying fully operational.
Now, while a replication factor of 2 safely handles a single node or disk failure, it's super interesting to note that Nutanix explicitly recommends configuring RF3 for storage containers at sites with high protection requirements. It's all about achieving optimal cluster resiliency. RF3 gives you that extra layer of protection. You've got the original data plus 2 copies. But keep in mind, that peace of mind does come at a cost, requiring more physical nodes and storage capacity.
Moving on to Section 2. Let's walk through FTP and RF, specifically how data and metadata mapping works. This table right here is the absolute anchor of our whole topic. Look really closely at how metadata replication scales up differently than your standard data replication, all based on your fault tolerance level. Your cluster relies on a data resiliency factor to keep things available, and that is heavily tied to your cluster fault tolerance level, whether you're running 1n/1d, 1n/1d, or the bfeed 2n/2d. Let's break down the baseline. Under a standard 1n/1d fault tolerance, using replication factor 2, the system fundamentally relies on keeping exactly 3 copies of your metadata. This configuration data is managed by internal services under the hood, like Cassandra and Zookeeper. And here's the kicker: because you absolutely must have 3 metadata copies to maintain quorum and keep the cluster intelligent, you are physically forced to have a minimum of 3 nodes in your cluster. Make sense?
But watch what happens when we scale up. The very second you upgrade to a 2n/2d fault tolerance, which uses RF3 so it can withstand 2 simultaneous failures, that metadata requirement jumps from 3 copies up to 5. This right here is the underlying secret to cluster sizing. Because you literally need 5 independent physical places to store that Cassandra and Zookeeper metadata, an RF3 or 2n/2d configuration directly drives your cluster node minimum up to 5 nodes. There's no way around it. You simply cannot do it with 4.
To put this into 2 really concrete examples for your exam prep. Imagine scenario A. It's a standard branch office running 1n/1d. They're using RF2, meaning they can survive 1 node or disk failure, and they only need a minimum of 3 nodes. Now compare that to scenario B, a massive mission-critical data center running 2n/2d. They need RF3 to survive 2 simultaneous hardware failures, which absolutely mandates a strict minimum of 5 nodes.
All right, Section 3, Node, Block, and Rack Awareness. We're looking at physical fault domains.
See, fault tolerance isn't just a numbers game. It heavily depends on the actual physical topology of your data center. A fault domain basically defines the blast radius of a hardware outage. You can configure a single node, a block, or even an entire rack as a fault domain. It's crucial to visualize the hardware here. A Nutanix block is a rack-mountable chassis containing anywhere from 1 to 4 independent nodes.
Since the nodes inside a block share power supplies and a backplane, an entire block can technically fail at once. Block fault tolerance ensures your redundant data and metadata copies are placed on nodes sitting in completely different blocks.
But what happens when things go sideways? When you enable rack or block awareness, the system naturally tries to spread your copies across those diverse domains. But look at this fallback mechanism. If a node goes offline and the system can't distribute copies across different racks or blocks, it doesn't just panic and crash. Instead, it gracefully falls back. It places those data copies on different nodes within the same fault domain, just to ensure you at least maintain your basic replication factor.
Next up, Section 4, Exam Traps and Edge Cases. Let's look at some operational boundaries. The NCP-MCI exam isn't just going to ask you for basic definitions. They love testing you on these edge cases, so let's navigate the danger zone together. Here are a few administrative traps that definitely caught my eye. First, the Prism UI simply does not give you a point-and-click option to change an existing storage container's RFS. You have to use the command line for that. Second, while you can upgrade your fault tolerance, right now reducing your cluster FT from 2 down to 1 is completely unsupported. And third, remember that hook from the very beginning? That tricky 1 and 1D fault tolerance explicitly requires a minimum of 2 disks per node to even function. Keep that in your back pocket.
Another crucial concept is how this system behaves under extreme stress. A degraded node is one that's basically partially unresponsive. When a failure has already happened and the cluster finds itself in this degraded state, remember this exact logic for the exam. The system will intelligently prioritize keeping your critical applications online and servicing I/O over immediately forcing a massive, full data resiliency rebuild. A rebuild could choke out your remaining resources, so application availability always takes precedence.
You've also got to be ready for self-healing sizing calculations. When a failure happens, the system automatically rebuilds that lost data onto healthy nodes, which means you need spare capacity. The exam expects you to know this rule cold. For a cluster with 2n/2d fault tolerance, your required spare capacity must always be equal to the capacity of the 2 largest nodes in your cluster.
Finally, Section 5. Key facts to memorize, the essential minimums.
Let's lock in a rapid-fire cheat sheet you can just sear into your brain before test day. Rhythmically repeat these minimums to yourself if you have to. RF2 needs at least 3 nodes and withstands 1 node or disk failure. The robust RF3 for 2n/2d strictly demands 5 nodes and withstands 2 simultaneous failures. And then there's the big exception we talked about, 1n and 1d. This level actually uses RF3 for the data, but uniquely only requires exactly 3 nodes, and it can withstand the failure of 1 node and 1 disk simultaneously. Totally unique.
And lastly, please never mix up the back-end math that drives everything we've covered today. Replication factor 2 requires 3 metadata copies and 2 data copies. Replication factor 3 scales that up, requiring 5 copies of metadata and 3 copies of data. That metadata requirement, that's the invisible tether dictating your physical cluster sizes.
As you head into your certification exam, consider how deeply understanding these strict minimums goes way beyond just passing a test. It's the engineering that ensures you never face catastrophic data loss in your real-world environments. So, with these blueprints fresh in your mind, are you ready to confidently calculate usable capacity and perfectly map out fault domains for your next cluster design? Good luck on your NCP-MCI exam. You've got this.